Thank you for attending. Welcome to my session. This is a very generic title, Java for AI. It's really Java platform features to AI, but that was too long. I would actually wish I was presenting from that couch down below there. There's a camera. It would be much more comfortable like Remy over there, but I'm standing here instead. Okay, let's plug in and go. So what I wanted to talk about is Java platform features that can enable you to build AI-like solutions on top. So we're not talking about AI solutions in the JDK itself. We're talking about building blocks that can enable you to build solutions like libraries that your users can use instead. So we don't want to embed specific solutions into the JDK. We want to be general in what we do. And so what we're trying to do is empower you to build better AI solutions on top of the Java platform. What does that mean? It could mean NumPy-like, Pandas-like, PyTorch-like. You can see a pattern here, Python, Python, Python. But it can also mean OpenAI, Triton, Gluon-like. I don't know if you're familiar with those, but OpenAI have been developing dialects of Python that you can code in a dialect of Python and it translates to very efficient GPU kernels. We are exploring stuff like that. It can also mean Onyx script-like, which is the Onyx community for machine learning model developing Python-like dialects to translate to Onyx models, and we can do the same things in Java with the features we're building. The key thing is these are features that only we can do in the OpenJDK community. We don't want to do features that you can do as libraries in the platform. We want to provide, again, we want to empower you. So they often require either updates to the virtual machine, the Java language, and APIs, all three together sometimes. And crucially, as I said in the keynote, they commonly bridge the gap between the Java world and the foreign world. What I'd like to do is for the Java to give a great big bear hug to all of the stuff that isn't in Java and let it idiomatically feel like Java when you're using it. So using these features, we're exploring GPU programming and machine learning for Java. And we are exploring it, even though we don't want to put these in the JDK itself, we're exploring it for two reasons. We want to ensure that the features we put into the platform are the right features and they're fit for purpose. And we want to show what is possible. If we can do it, you can do it too. So if there's one thing to take away from this presentation is the features I'm going to describe, they interconnect in ways that can enable you to build powerful libraries and applications greater than the sum of the parts. Also, of course, I'm biased because I work in the Java platform group, but over the period of time of the 6-month releases that have gone on and on, it's like an impulse engine, boom, 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 like this, and it's getting really good to prototype solutions out. It's getting really good to code in. It's not perfect by any means, but we're incrementally improving it over time. And I've been able to rapidly prototype in this environment more so than ever before. Okay, so here's what I'm going to try and do. I'm going to try and talk about the projects, the features they enable, and I'm going to try and focus them on a use case. And the use case is a matrix API, which you can think of as a prototype NumPy-like API. And I'm going to explain each of these features and how they can be used and build on top of each other to get better and better solutions, both for the developer productivity and program performance. So I'm going to talk about Panama and the foreign function memory API, and I'm going to describe how you can reach out to a native linear algebra library called Bliss and wrap in an idiomatic Java API. And then I'm going to talk about Panama and the vector API and show how you can improve the performance of matrix operations on the CPU using SIMD. Now, the problem is I have far too many slides for 50 minutes, so I'm going to probably have to skip some interesting points in this narrative. We'll see how fast I go. Excuse me. I'm probably going to have to skip the descriptions around the float 16 support we've added and skip the descriptions about the heterogeneous accelerator toolkit, which was talked about yesterday by Anna and Liz. And I'll focus on Babylon and code reflection and describe how we can express matrix operations using regular Java code without losing performance. If I get time, I will dive into one of these other topics as well. So let's focus on the Panama's foreign function and memory API. If you're not familiar with it, it's a fast, safe, and productive way to interoperate with foreign or native libraries. It's in nearly every way better than JNI, for sure. And I've used both, and I don't want to use JNI ever again. And it's final since Java 22. And there's been incremental improvements afterwards in terms of its performance. The JIT's got better understanding how to optimize expressions using this API and so on. It really is quite good. Combined with the API is a developer productivity tool called JExtract, which allows you to generate pure Java bindings from C header files. And this speeds up the mechanical part of the development, leaving more time for us to do the creative part, which is to take that API and use it and wrap it around something that's a pleasure to use for Java developers. So here's the architecture of what I'm going to describe here. A Java binding using native Bliss. Bliss is a linear algebra library that has won a number of awards for its quality of code and its performance of code for implementing linear algebra operations like a generic matrix multiply, matrix inverse, and so forth. It's extraordinarily efficient. It's very carefully engineered to maximize the use out of the CPU, both in terms of the way the CPU architecture is in terms of memory, but also in terms of what vector instructions are available on the CPU. So if someone's already written a really efficient matrix multiply, I don't have to implement it myself. I can just use it. So how do we use it? So we have native Bliss at the bottom. We have the JDK with the foreign function memory API. We have a Panama Bliss binding. By using JExtract on the Bliss header file, we generate the binding, and then we can write to it directly. So an example of how you do this is in Bliss. If you want to create a matrix in Bliss, it's a bit confusing, the terminology. You call this BLI_obj_create method. The obj in Bliss means matrix, effectively. So it's a way of allocating a matrix, 2 dimensions, with a certain shape and a certain layout. That's what you do. That's what you call. And you give it a pointer to an obj structure that fills in the details of the structure, if you're familiar with C. So we need to call that. So we take the Bliss header file. You see the definition of the BL object create. We run JExtract on it. That gives us the Java version of that method, the binding. And then we link to libbliss through Java, and then we write our code directly using it. So here I have a simple Java program with main method using the new concise method, using the concise way of expressing Java programs. And here we can see we're calling that binding method BLI object create. And we see we have to allocate the ob structure in memory off heap, and then pass it along as a value, as a variable A here. And then we can call other methods on it, like randomize the elements in the matrix, print it out, and then we have to free it. So even though we've confined our scope of our program in an arena, a confined arena, which is thread confined, and we allocate our obj structure in that confined arena, Bliss is managing the allocation of the buffer of elements underneath where they're stored, and so we have to free it explicitly here. So I'm effectively, what I'm doing is I'm writing C code in Java. So on the left-hand side is the C using the Bliss Object API, and on the right-hand side is Java using the bindings. And it's almost one-to-one similar, except I can't allocate structures on the stack. I have to allocate them off heap, like so. And so they're pointers instead. But you can see the comparison between the two. And I don't want to write like this at all, but it's the stepping stone to do something better, because I do not want to generate the bindings by hand, what JExtract did to me. That's a lot of mechanical work. That's what computers are great at. So what I want to do instead is put another layer on top, which is a matrix API, which is a library that uses the Panama Bliss bindings underneath. And then I can write my application on top of that. So instead of using the Java bindings on the left-hand side, I can use my matrix API, which just collapses it all. Instead, I could just allocate my matrix. I give it the arena where I want to allocate both the Bliss object structure and also the buffer of elements, maybe. And I just do the thing that you'd expect as an API from a Java developer to do. So it all collapses down. And if we wrap it around the arena and we look at the scope of it, it becomes simpler still. On the left-hand side, using the bindings, I don't need to allocate the obt structure. I don't need to call create. I still need to call the gem if I want to do a matrix multiply, so I can reach out to matrix multiply, but I can wrap it in things that accept the matrix API rather than the memory segments that point to the Bliss's version of the matrix itself. And plus, I don't have to free it. So the scoping is, as soon as I hit the end on the right-hand side, it frees the matrix, and however I manage the memory, it will deal with it all like that. That's how we want to code here. And of course, it's a confined arena. If I wanted to use an arena which is just GC, I can remove the try-catch block and it would work, and then the off-heap memory would get freed when things become unreachable. You have to be careful with the latter because GC is non-deterministic. So if you want determinism on your allocations and determinism on your deallocations, you'd use the confined arena if you can. But sometimes you can use both. You can intermix them. So here's what's going on when I call new double matrix. I'll try and unpack what's going on. I say I'm allocating a new double matrix and passing in an arena, and I'm saying it's a 3x3 matrix. Like so. So there's a split between what goes on heap and what happens off heap. So on heap, we have an instance of double matrix, an object on the heap managed by the GC, and it has a bunch of fields, and there are two fields of interest here. One is the memory segment that points to the obt structure, and a memory segment that points to the buffer of elements. And you see that the memory segment is another object on the heap, and then the two memory segments have a length and a pointer. These are native memory segments. So they have a length of how many bytes I have, and a long value whose value is actually a pointer to the off-heap memory that's been allocated. And so they point across to the off-heap memory, which is the obt structure which is initialized through BLI object create. And it also has a void star pointer to the buffer of elements as well. So the Java side knows about the buffer of elements in the matrix, and also the Bliss side shares the same pointer as well. And then those elements are laid out in a certain way, and the Java side and the native side both know what those layouts are. So in this way, in this case, we're talking about column major order. And so we go down the column and they linearize like that. And so both the Java side and the native side know exactly about this. And this is good because we can do work on Java side or the native side, depending on where we want to do the work and whether it's better to do it on the Java side or the native side. So what I've shown is something that wraps the Bliss Java binding in an idiomatic Java API, so we don't have to write like C code. And crucially, there's no size limits on this, as you previously experienced with primitive arrays and byte buffers. The size can be greater than integer.max value in terms of length of the size of the matrices. And as crucially as also, there's zero copy between the JVM and the Bliss native library, because we're just sharing pointers. So this provides an easier and safer API for memory management. We don't need to malloc or free the Bliss objects or their buffer of elements. And so we can use Bliss for the level 3 BLAS subprograms that are the ones that require a lot of engineering to get right and be performant, both on matrices of large matrices and skinny matrices and all the kinds of things you might have to input into this. It's great for this, great for pseudo-inverse as well, but it's not so great for the sort of level 2 like BLAS subprograms that don't do this sort of ON3 kind of operations, but they're sort of ON or O1 or something like that. And Java can shine there. So we can use Bliss for the complex stuff, and we can use Java for the simpler stuff, and the stuff that Bliss does not support. So we can sort of express unary, binary, ternary test reduction operations on matrices using lambda expressions, higher order functions. And by using this, we don't have an explosion method. Say we wanted to add the elements of two matrices together. We don't have to have an add method, a sub method, a mul method, and so forth and so on. We can express the intent using a lambda expression. And of course, Bliss does not support higher order functions as well, so we can't do this in Bliss. We can use Bliss for the stuff it supports. So here's an example of what I mean, which is column mean. So it takes a float matrix in, we allocate a vector of the mean. So what I want to do is calculate the mean of the columns of the matrix. And so we create a vector of mean, which is of dimensions of 1, the A columns. And then we call a method called reduction column. And I pass in a lambda expression that just sums things up. Like so, that expression, I don't want to add, say, a reduction column sum. I can express that as a lambda expression, like so. And then I can do a unary division operation that produces the actual mean afterwards in place, and then I can return it like that. So there's two, again, I don't have to add an element-wise division operation. I can just express it in a lambda expression. I think that's a great way to code. It also means we don't have to do operator overloading on matrices as well, which I don't think we're ever going to do in the JDK. So here's another way, here's a more sophisticated thing which we can use the mean to produce a standard deviation of the columns as well. So I can compute the mean, I can create another vector for the standard deviation, I can do something if it's bias corrected or not, and then I can do a reduction column that says, what is my initialization for the reduction, how am I going to do the reduction, and how am I going to produce the result after I finish. So there's 3 different lambda expressions here. One which says, okay, I need to create 2 values I need to keep around, and when I'm doing the reduction, I need to do a little bit of calculation and accumulation, and at the end, I finish up like that, all nicely expressed as clear lambda expressions again. So thinking about this more generally, we have binary operations for matrices ABC of the same dimensions. We can do element-wise, and we can add them together. So this is what's going on underneath the covers. So we've got 2 matrices A and B, and we can add them together element-wise, like so. But what if B is a singular matrix, a row matrix, or a column vector instead? What if they don't have the same shape? Well, we can do broadcasting. So we can broadcast B into B prime that is the same dimensions of A. And this, if you're familiar with pandas or NumPy, you'll know what I mean here. So you can broadcast a scalar into the same shape and then provide the operation and so forth for the broadcast row and column vector, like so. Pretty straightforward. And so you can do a broadcast on the row vector, a matrix A, which is 5 by 3, a matrix B, which is 1 by 3, set the values, and then you can do an element-wise on it, and it will work too in the same way as I showed before. So here's a representative implementation of this element-wise row vector. So you'd loop over the columns, you would get the value for B out of the vector, and then you'd loop over the rows, and you would get an index into A, you would access it through A's buffer, and get the value of A out. You would apply A and B together to get C, then you'd store it in the matrix C in its buffer, like so, using memory segment operators. So these get at index and set at index are operations on the memory segment I showed connected together, like so. But that's a representative thing. You've got 2 loops going on here. But the problem is the inner loop is going to be hard to optimize, because if you've ever hit sort of a performance cliff, if you throw loads of lambda expressions at the same call site, you'll notice your performance will drop, because we can't optimize in here, because we can't inline after a certain number of points, because there's going to be different code for each float binary operator argument coming in. We need to specialize this loop. So here's a simple benchmark, JMH. On the setup, we have a Boolean parameter which says, am I going to pollute? So before I actually run the benchmark. And so I'm just going to call element-wise on this with the same lambda expression. I'm going to pollute it. And so the hotspot JIT knows there's a bunch of different, it doesn't distinguish between the same lambda expressions are different. It all thinks they're different. And so it doesn't know how to optimize this anymore. And so the scalar of a benchmark is just a simple scalar element-wise operation, like so. And if I run it with the pollute false, I get 16, it takes 16 microseconds per operation. But if I run it with pollute, the performance drops right off the cliff, because we can't optimize it. We can't inline, we can't loop unroll, and so forth like this. So this is known as the inlining problem by Cliff Click, and it's also known by the loop customization problem by John Rose. This is an old problem, and it's still very relevant today. So I'm going to explain how we get to this point, but I'm just going to go into the Vector API now. We're going to use that in a bit. So the Vector API is a Java runtime that has supported implicit SIMD. The Java runtime itself has supported implicit SIMD for a number of years. So the C2 JIT compiler has very rich support for a lot of CPU ISAs out there and vector hardware instructions. And it can auto-vectorize. It's pretty good at this. And it can do it using the easy parts of the ISA, the easy instructions, transforming loops into data parallel loops. But trying to second guess what the JIT does in the hope of squeezing out more performance and providing a programming model how you understand the JIT works is not the right way to go, because it might work on a good day, and when you upgrade, it might fail on another day. And the JIT cannot access the more irregular parts of the ISA, the more interesting parts where you might want to optimize. The cost to support that increases, it becomes more fragile. But a lot of high-performance data algorithms will often leverage permutations or shuffles, fuse multiply adds, and so forth. We want to access those. So the Vector API provides explicit portable access to the back end of each ISA in a explicit SIMD model. So you're not sort of coding into a sort of implicit SIMD model and guiding the JIT what to do. You're being very explicit and telling the JIT what to do. It's very similar to Google's Highway library in C++. A key thing is the back-end investment we've done here pays off twice. The auto-vectorization and the Vector API share the same common back-end, but only both make sense. Either or does not, depending on what you want to do. And so we can implement high-performance data parallel algorithms in Java, such as dot product, matrix multiply kernels, if you don't want to use the Bliss side, but also some things like UTF-8 validation or vectorized arctangent, etc. In theory, we haven't tried this yet, we may get there, we can potentially replace some of the intrinsics in Hotspot that are implemented in sort of hand-coded assembler on each platform with cross-platform portable code that compiles to the equivalent hand-coded assembler, so we potentially can eat our own dog food. So here's a really simple example, a simple scalar code on the right that does some computation. Very straightforward. And here's the code, left, and here's the code on the right, like this. Now, you don't want to write this code on the right in many cases. This is for advanced developers. This is for the library developers. Your users should not write this code at all. Users should write the easy code on the left. But if you want to squeeze out performance, you may have to go to code on the right. And in this case, you see the expression is using vectors. So I'm looping over, striding over a number of strides, getting the vectors out and operating in data parallel explicitly like so. Here is where we may be able to use operator overloading in the future. Don't know yet, to make it a simpler expression. So we loop over the strides, do our same computation, and then we have to process the remaining elements that don't fit into the sort of units of striding we're doing. Now in this case, actually both sides will produce and should produce the same code because it's a simple problem, and that's okay. The one side is more explicit, the right side is more explicit, the left side is implicit, and sometimes the left side will not work for various reasons. But they should both produce the same code. Here's an example I'm showing, which with loop and rolling off, just to show you the sort of loop. And you see it's striding by 8 steps at a time, because this I did this on an Intel Mac a while ago, which had AVX2 on it, that allows you to fit 8 floats into 256-bit vectors, like so. So we want reliable performance with the loops I showed before. And so to do that, we need to operate on linear regions of memory for SIMD operations. You have to operate on linear regions of memory to load. It's called cache coherence, pulling data from memory, and the vectors load from linear regions, like so. And we need to solve the inlining problem in this context, not generally. So we need to write specialized code that iterates over the column of A for each iteration performs a SIMD element-wise operation using the vector API. So to get an idea of what's going on here in terms of memory, let's go back and remember the obt structure and the memory segment both point to that buffer of elements, and it's in column major order. And we can immediately see there's sort of regions of linear memory for the columns. So there's an opportunity here for each column to do data parallel processing on each column. There's actually an opportunity to do thread parallel over the columns as well, although I'm not going to talk about that. You can see, if you know the sort of layout, now here's our opportunity to parallelize. So here's the representative implementation again I showed earlier. And so what we need to do is somehow move the implementation of that inner loop up to the float binary operator instead, where it's specialized for its particular operation. So the hotspot compiler gets out the business of specializing that loop itself. It can't do it. We need to move it up. So we have to do some tests here. We have to say, is A and C in column major order? Yes, it's okay. And is our float binary operator a specialized kind of operator that supports an additional protocol that I know I'm going to operate in this special way? And if it is, instead of calling the inner loop, I can jump to a special method on that specialized operator, the binary broadcast kernel, instead. And I can call it with the buffer of A, the buffer of C, the value of B I loaded, and crucially, I can give it the offsets to the columns in memory, because I know what they are at this point. And so I can implement a specialized version of my loop. In this case, we're just talking about multiply, similar to the example I showed before, where first of all I do my vector loop, performing the multiplication, and then I perform a scalar loop at the end, so I can specialize this. Notice at the top, I get my memory segment in A, and I slice it to the column, and I bound it to the column size, so I can never go outside the column size. If I have a bug in my program, I'll get an index out of bounds exception, because I slice A and C before I operate on them. Then I operate directly on the memory segments as before. So performance is actually quite good in this case. Again, I'm using the example I showed before, scalar, but then I have a scalar kernel and a vector kernel. So the vector kernel is the code I showed before, but you can also run a scalar kernel without the vector API, like so. And the scalar kernel and the vector kernel, again, should perform the same way. But actually they're not, because I think there's a bug in the auto-vectorizer in memory segments, so I need to go look at that to fix it. But the point is, they're not, in this benchmark, the pollution is not, if we pollute the call sites, these kernels, using the kernels, we're not impacted by that problem. So we've solved, in this case, the inlining problem. There's a more complicated, perhaps more real-world, in some sense, case where we can show this using arctangent instead. There's an algorithm for arctangent in this old library called Cephes, and it's in C, and I converted it to Java both for scalar and vector API implementations. And I implemented that And then I also can show the version of using scalar using math.atan. And I can also show the version of using the vector operators atan, because you can use the vector API with arctangent too. And if the hardware supports it, or library supports, the hotspot supports it, we can use optimized vectorized atan underneath the covers. And it just so happens we've integrated the Sleeth library into hotspot that has these optimized vectorized algorithms for transcendental functions. So Cephes trades accuracy for performance, and the Java platform implementations are more accurate but slower. So we can do benchmarks for these as well. So on the left, I have the scalar Cephes implementation, element-wise, atan, and then on the scalar math, I'm calling math.atan. On the other side, I have two kernels, one which is called the vector Cephes kernel, and one which is called the vector math kernel. And you can see from these benchmarks, the Cephes, scalar Cephes and scalar math, you can see Cephes is faster than scalar math, but you can see that the vector Cephes kernel is really quite fast compared to its scalar, because we've optimized it and solved the profiling problem as well. But the vector math kernel is not bad too. The Sleeth implementation is doing quite well there as well. But the Cephes algorithm is simpler and less accurate. We get more performance. And maybe accuracy is not what you need here, and you can trade accuracy for performance, like so. Now, I'm not going to show the implementation of the ATAN. It's using more extensive features of the vector API, and it's a more realistic use case that the auto-vectorizer cannot auto-vectorize. Okay, so let's go on to Babylon and code reflection. So code reflection is all about extending Java's reach to foreign programming models with an enhancement to reflective programming in Java that's called code reflection. So reflection today only gives you access to the surface details of a program. Given a class, you can reflect over it and say, what are my methods? What are my fields? But you can't say, what is the code in my method? Or what is the code in the Lambda expression? So we extend Java reflection and give deeper access to give access to the code in a method body or a Lambda body at runtime. And we call what you get access to a code model. It's a symbolic representation of the code. It's different to bytecode, and it's different to the Java C's AST compiler. And it's really a tree-like structure, similar to Java C's AST, but it's more suited to analysis and transformation. It's more like the structure you'll see in MLIR, which is part of the LLVM community. So a foreign programming model is one that is not the Java programming model as specified by the Java language. So you can think of differentiable Java programs. The Java language specification and Java virtual machine specification, they know nothing about that. They know nothing about GPUs. They know nothing about machine learning models. What we want to do is embed that knowledge into Java libraries instead. We cannot specify what GPU programming models are or differential programming models are in the specification. That does not scale. We can't grow the platform like that. So here's a quick example. Say I have a function to differentiate on the left, simple mathematical function, and I want to produce the partial differentiations of that, the partial derivatives of that, and compose into a gradient function. And I'm going to do forward mode differentiation because I'm not smart enough to do reverse mode differentiation, and I can't fit it on a slide anyway. So on the right-hand side are my hand-coded versions of the partial derivatives of this with respect to the independent parameters x and y. Trust me, I think this is true. I've checked it. I've simplified it. But it's hard work. You shouldn't have to do this. Even simple expressions like this are error-prone. And if I change the left-hand side, I'm going to have to change the right-hand side. I don't want to do that. So what you can do instead is you can write a little library that does what I had to do by hand and effectively do automatic differentiation, forward mode, which is pretty simple to do. It's a chain rule, turn the crank, a bunch of rules. So on the right-hand side, we can look up through Java reflection, APIs today, we can get the method for f. And then using an API from Babylon project repo, we ask it, do you have a code model? And it does, because we've annotated the left-hand side with code reflection to say, this is of interest, I need to do something special here in the compiler to produce code models that are accessible at runtime. So we can get our code model, and then we can have a library that implements a forward diff method that takes that code model and produces the two code models for the partial derivatives I had to implement by hand. And then once we get those, so code models in, code models out, so we get a symbolic description of the derivatives. And then we can say, hey, compile those derivatives into a gradient function and call me, like so. And so the library is doing all the heavy lifting here. And so there's many opportunities to implement all sorts of interesting things using code reflection with this facility. So writing element-wise kernels by hand, like I showed earlier, is really painful. We don't want developers to do that kind of thing in general. We just want to write ordinary Lambda expressions. So we can use code reflection to do that work for us. So we can reflect over the code of the Lambda expression, the element-wise operations, and we can translate that to a vector kernel equivalent to what we wrote by hand. And we can preserve the simpler API and get reliable performance. So we can take our multiply Lambda expression, just A times B, and we want to go to this code, a specialized code on the right that I showed earlier. We do not want to write the code on the right at all. So what we need to do first of all is translate this scalar Lambda expression into a vector API expression, like so. It could be more complex, so we might be writing a special limited constrained auto-vectorization that if it can't auto-vectorize, it fails and tells you as a library. And then we want to take that, and on the right-hand side, instead of that explicit code, I can write a template, and I can annotate it with code reflection and say, I want to reflect over this. And crucially, in this template, there are holes in the template I've highlighted, vector of t and scalar of t, where I want to substitute my explicit expressions. So even if I'm using code reflection, I do not want to write the code that builds that symbolic representation by hand. I want to leverage the compiler. The compiler is really good at doing that, so I can just write it in Java, and it's a template, but I want to translate it into what I showed previously. So I want to replace the scalar expression A times B with that method call there, and I want to do the same for the vector API expression, like so. So I basically reflect over my template, and I translate, and I'm doing it twice. So I reflect over the Lambda expression and translate, and then I use that results, and I stuff it in the others, like so. And then we get the result again, but we don't have to handwrite it. So here's a representative implementation of how that might work. So we have a reflectable float binary operator. It extends float binary operator, but it also extends something called quotable, which is the equivalent of serializable, but for code reflection. It's saying, hey, compiler, this is of interest. I need the code model for this accessible at runtime. And then internally, I do a similar thing, checking A and C to see if they're the right shapes and orders that I can do this sort of linear memory operations in. And then if it's right, I go lambda to kernel, doing all the things I described above. And if it's done it once, it can cache it, so it doesn't need to do the same work again. It can cache things here. So this lambda to kernel might be actually quite efficient after the first run. And then I can call the kernel binary broadcast scalar on that, and I get everything nicely working and nicely speeded up. So in summary, what I do is I reflect over the scalar lambda, obtaining its code model. I translate the scalar lambda code model, producing a vector lambda code model, and perform element-wise vectorization on it. And then I reflect over the template method, obtaining its code model, and I translate the template method code model, producing the executable code model. and I replace invocations to method scalar t with the results of inlining the scalar lambda code model, and I replace invocations of scalar t, and then I replace invocations of a method vector t with results of inlining the vector lambda code model. It's a bit of a mouthful, but you can see the sort of logical steps going on here, very clear steps. So I don't expect you to understand this too much here, what's going on, but this is real code I implemented to do this translation of the template. It's not a lot of code. What's going on here is we have a code model and we want to transform it. And it's going to linearly go through all of the structure, and it's going to say, well, if I've got an invoke operation and the invoke operation descriptor is scalar t, please inline me the scalar opcode model. Otherwise, if it's an invoke operation and it's describing an invocation to vector t, please inline me the vector opcode model, like so. And that's it. Nicely compressed. This kind of transformation is similar to the class file transformation API, if you're familiar with it. It's a flat map style transformation. It takes an operation in, and you can replace it with 0 or more operations in your output. That's essentially what's going on. Okay, I actually have some time, so I'm going to go back, and I want to... Okay, let's have a question. Do you want to see the float 16 stuff, or do you want to see the heterogeneous accelerator toolkit stuff? Hands up for the first. Okay, hands up for the latter. God, it's equal. I'm gonna do the latter first, because I think that may be actually more intriguing in general to folks. Let's see if I can get through this. And how do I unslice it? Unskip. I think I can unskip all these. Yep. All right. So we talked about execution on the CPU. What if we wanted to execute those element-wise operations on the GPU instead? Say if the cost of copying the data from the CPU to the GPU was low enough, and the cost of performing the operation on the GPU was high enough, so we got a performance benefit, which happens when there's large amounts of data. Large amounts of data, but very high operations on the GPU, or depends on the GPU hardware that makes that copying efficient. So the idea around a heterogeneous accelerator toolkit is to develop portable Java code where we can debug on the CPU and run on the GPU, because debugging on the GPU is a real pain, apparently. And it uses code reflection. It uses it to translate Java code to foreign GPU code, and it uses it to optimize the data movement between the JVM and the GPU, because copying is costly. If it's already on the GPU and we know it, we don't need to move it back and forth if we're making multiple kernel calls. And it can also optimize the scheduling of the execution of GPU code on the GPU as well. So if we can look at the whole call graph, we can say, hey, we can call these things asynchronously and wait at a certain point until we get the result back, but we need to operate on the CPU and then get back again. And crucially as well, it uses FFM to call the GPU compilers and GPU runtimes. So there's 4 things in HAT. One is a kernel parallel programming model familiar to GPU developers. And Java code is translated to GPU code and run on GPU. It can also potentially support other programming models. I mentioned OpenAI Triton. You can annotate loops like Tornado VM, potentially other programming models like annotating loops like Tornado VM as well. It's not limited to this programming model to generate kernels. As a compute programming model that scopes and coordinates the calls to kernels. So the code is run on a JVM. You can write natural-looking Java code with loops and conditionals. And this is where we can see into it and optimize the data movement and kernel scheduling. It provides a data model that describes the data layouts between the JVM and the GPU, so they both know about it, and it's a both very clear contract, and it's all off heap. So if you're allocating on the CPU, it's off heap, a stable pointer. You can pass that pointer to the GPU or copy it into GPU memory, depending on the GPU architectures. And last but not least, and probably most importantly, there's a pluggable accelerator abstraction, so GPU vendors can showcase their device's capabilities. What we'll provide in 1 and 2 is the ability to express GPU code that can translate into very efficient GPU code, write Java code that can translate into very efficient GPU code, leveraging all of the hardware capabilities on that GPU. That's the aim. And so it's important that we can engage with GPU vendors that have the knowledge on how to leverage the maximum out of their hardware. And crucially, the abstraction can also provide sequential implementations for debugging on the CPU. But we could also provide a multi-threaded data parallel using the vector API for optimal CPU utilization. If you don't have a GPU, but the model is capable of being translated and executing on a CPU in sympathy with the CPU's memory hierarchy and vector instructions, we can do that too. And so there's another use case for code reflection and the vector API here as well. So here's the architecture. Native-wise, we have the CPU and JVM. On the left, we have the GPU or FPGA and the accelerator framework like a CUDA, OpenCL framework native. And then on top of that, we have the JDK and the HAT library and the accelerators in there and the HAT code using FFM and code reflection. And then on top of that, we have the kernel and compute code written by the application. And you can have a bunch of accelerators here for each different kind of hardware. AMDs, NVIDIA, AMD CPUs. Zen 5 is a really excellent CPU. If you do it just right, this can crank out a bunch. It can really compute very efficiently. Here's an example of a HAT showing the game of life. I want to show this because I really want to show it on the big screen. All right. So I am going to run a demo, which is the game of life. And first of all, I'm going to run it on the CPU. And I'll show the code afterwards. We should have time. So it's a simulation of digital clock in life. So it loaded up the world, the grid, and it's going to apply the rules of the game of life. Each iteration, it's going to show a new iteration. And if I start it up, we'll see the number of generations per second. This is running on the CPU, and if the CPU should be maxing out at some point, you can see it down there on the activity monitor. But it's only doing like 8 generations per second, so you can't see the digital clock emerge. So let's run it using the OpenCL backend, because it's a Mac, it has an OpenCL implementation on it, can leverage its GPU. And we start running, and we immediately see a boost. And we immediately see the emergence. If I keep talking long enough, you'll see the digits emerge for 12. So it's producing an orders of magnitude more frames per second, like so. Because this is embarrassingly parallel, and the GPU is excellent, and there's gazillions of threads being able to compute this. So you see the 12 appear, and if you wait long enough, you'll see the 1 appear, but we do not have time for that. So I can explain quickly what's going on in life here. So we create an accelerator. This is it knows that I'm an OpenCL. It looks up what my GPUs are. It knows I've got an OpenCL GPU, compatible GPU. And when we run it for a compute, the scope of the compute is this reflectable lambda expression that can call this method, which is annotated with code reflection as well. And this is code running on the CPU that is in a loop and doing the iterations of the game of life. And for each iteration, it dispatches a kernel that produces a calculation, and then it does some double buffering to exchange the sort of worlds of, I've done this iteration, I'm going to show the next one I can do. It flips between it, so I don't have to copy too much. Then it asks, if I'm ready to view, I will update it. But if I'm not, I'll just keep going, like so. And then we dispatch to the kernel, like so, which is another lambda expression which expresses the scope of the kernel. And when we call compute life, more methods, so forth like this, and then we get to our eventually our code like so, which implements the game of life logic like so. It's not bad Java code. It's not as natural in terms of interoperating with the arrays yet and so forth, but we're getting good. And if we look at the output here, we can see that it generated a bunch of OpenCL structures which describes the ABI I was talking about, the data model, and the OpenCL C code, like so, generated, which is actually pretty similar to the Java code in that way. So it translated the Java code to OpenCL C code, and idiomatically so, which means the compiler can do this. The OpenCL C compiler is very good at compiling this kind of code. All right. So that was hat. Also, I ran it with the minimize copies, which basically optimizes the looks at where data is moving and can optimize it. If I run it without minimize copies, it runs slower because every iteration I'm displaying, but we can iterate faster over the game of life than we can displaying it. So I'm doing in the prior one, I was iterating a lot faster and then taking a sample out to show you. But in this one, it's doing it at the same time, so it's 37 frames per second, effectively. All right. I'm going to have to skip that. I'm just going to say that we can do the same thing we did on the CPU and generate GPU kernels through code reflection and execute them on the GPU instead. So effectively, we can think about it having a scoping. Rather than the arena, we can have a scope of where am I doing my compute. And in there, we can encapsulate the code reflection generation of these little lambda expressions and target the CPU or the GPU underneath, depending on what our sort of accelerator scope is under the covers. Okay, that is it. I have to do an advertisement for Java 1 next year. Should be good. And sorry, I do not have any time for questions, so come and talk to me afterwards, but I'm going to be in the Architecture panel in about 20 minutes, so you could ask there or ask me after that. Okay, thank you so much.